Hello everyone, today we will study change of basis. First of all, let me introduce coordinate. Let V be a finite dimensional vector space, and let S equal to V1, V2, Vm be a basis in V. Then, for all V in V, vector V can be expressed as a linear combination of V1, V2, Vm in exactly one way. That's called a uniqueness of basis representation. That's what we learned last class. It says every vector in V can be expressed as a linear combination of all vectors in a basis in exactly one way. That's called a uniqueness basis representation. Now, suppose the vector V equal to k1 v1 plus k2 v2 plus kn vn for some scalars k1, k2, kn. Then these scalars k1, k2, kn, they are called the coordinates of vector V with respect to base x. And if I write k1, k2, kn as a vector, that's called the coordinate vectors. That's called a coordinate vector of V with respect to s. That's called a coordinate vector of V. That's called a coordinate vector of V with respect to s, denoted by V sub s. V sub s equal to k1, k2, kn. V is the vector. S is the base. S is the basis. V is the vector. S is the basis. And k1, k2, kn, that's the coordinate vector. So V sub s equal to k1, k2, kn. That's called a coordinate vector of V with respect to s. Next, let's create an example. Let W equal to 1, 1 be a vector in R2. Part A. Let S be the standard basis in R2. Find the coordinate vector of W with respect to S. Here, how can we find the coordinate vector of W with respect to S? First of all, S is the standard basis in R2. That means S has two vectors. V1 equal to E1, where E1 has 1 in the first component, 0 in the second component. V2 is the same as E2. E2 has 0 in the first component, 1 in the second component. That's the standard base S in R2. Next, in order to find the coordinate vector of W with respect to S, we try to write W as a linear combination of V1 and V2. For small numbers, we can try it out. Here, W is 1, 1. 1, 1 can be written as 1, 0 plus 0, 1. And 1, 0 can be written as 1 times 1, 0. 0, 1 can be written as 1 times 0, 1. So here, that's V1, that's V2. I can treat this number 1 as K1, treat the second number 1 as K2. So here I write W as K1 times V1 plus K2 times V2. The scalars is 1 and 1. So the coordinate vector of W with respect to S is K1, K2, which is 1, 1. Part B. Let B be the set of two vectors, -2, 1 and 3, -1. Let B be a basis in R2. Find the coordinate vector of W with respect to B. Find the coordinate vector of W with respect to B. What can we do here? In order to find the coordinate vector of W with respect to B, we try to write W as a linear combination of these two vectors in B. Let me call this vector V1. Let me call this vector V2. We try to write W as a linear combination of V1 and V2. What can we do here? We try to write W as a linear combination of K1 V1 plus K2 V2. How can we solve this vector function? How can we solve this vector equation for K1 and K2? For a vector equation, a shortcut to set it up is I can put a component of V1 in the first column, put a component of V2 in the second column, and put a component of W in the third column. And then use Gauss-Jordan elimination to solve for K1 and K2. That's a quick way to set up a vector equation. I put a component of V1 in the first column, put a component of V2 in the second column, and put a component of W in the third column. Then use Gauss-Jordan elimination to solve this equation for K1 and K2. Here, let's use Gauss-Jordan elimination. Let's use Gauss-Jordan elimination. I can first of all interchange row 1 and row 2, make leading one here. I get 1, -1, and 1 in the first row. -2, 3, and 1 in the second row. Next, I can multiply first row by 2, add it to the second row. I get 1, -1, and 1 in the first row. 0, 1, 3 in the second row. Next, I can add the second row to the first row to make 0 here. I get 1, 0, 4 in the first row. 0, 1, 3 second row. That means K1 equal to 4, K2 equal to 3. That means K1 equal to 4, K2 equal to 3. So W equal to 4 times V1 plus 3 times V2, which means the coordinate vector of W with respect to B is 4, 3. The coordinate vector of W with respect to B is 4, 3. We can check the answer. If we check the answer, we take 4 times V1, 3 times V2, we must get W. Let's check. 4 times V1, 4 times V1 plus 3 times V2. We must get W. Let's check. V1 here is -2, 1. V2 is 3, -1. Let's check. If I multiply 4 times -2 is -8. 4 times 1 is 4. 3 times 3 is 9. 3 times -1 is -3. Then add, we get 1, 1. That's the same as W. So that's how we check the answer. Take 4 times V1 plus 3 times V2. If the calculation is correct, we must get W. Now here we can see that in part A, if we choose the base to be the standard base, then the coordinate vector of W is exactly the same as W itself. If we choose a base to be the standard base, the coordinate vector of W with respect to S is the same as W itself. So that's no coincidence, that's a rule. If S is the standard basis in Rn, then in general, for all V in Rn, the coordinate vector of v with respect to s is the same as v itself. If S is a standard base in Rn, then for all V in Rn, the coordinate vector of V with respect to S is the same as V itself. Here W is a vector in R2, and S is the standard base in R2. Then the coordinate vector of W with respect to S is the same as W itself. That's not coincident. This is always true. Next example, let P of x equal to 4 plus 2x plus 9x squared. Part A, let S be the standard basis in P2. Find the coordinate vector of P with respect to S. Here, how can we find the coordinate vector of P with respect to S? S is the standard basis in P2. We know that the standard basis in P2 has 3 vectors, 1, x, and s squared. That's the standard basis in P2. In order to find the coordinate vector of P with respect to s, I try to write P as a linear combination of 1, x, and s squared. Let me call these 3 vectors P1, P2, and P3. I try to write P as a linear combination of P1, P2, and P3. So I said for small numbers we can try it out. Here P of x is 4 plus 2x plus 9x squared. That can be written as 4 times 1 plus 2 times x plus 9 times s squared. We know that 1 is the same as P1, x is the same as P2, s squared is the same as P3. So that's 4 times P1 of x plus 2 times P2 of x plus 9 times P3 of x. Here I write P of x as a linear combination of P1, P2, P3. And their scalars is 4, 2, and 9. So the coordinate vector of P with respect to S is the scalars 4, 2, and 9. 4, 2, and 9 form a vector. That's called the coordinate vector of P with respect to S. That's called the coordinate vector of P with respect to S. That's part A. Part B. Let B be the set of 3 vectors. 1 plus x plus s squared. 2 plus s squared. And x plus 2s squared. Let B be a basis in P2. Let B be a basis in P2. Find the coordinate vector of P with respect to B. Find the coordinate vector of P with respect to B. Here, in order to find the coordinate vector of P with respect to B, I try to write P of x as a linear combination of these 3 vectors. Let me call these 3 vectors P1, P2, P3. Let me call these 3 vectors P1, P2, P3. I try to write P as a linear combination of P1, P2, P3. So here I set P of x equal to K1 times P1 of x plus K2 times P2 of x plus K3 times P3 of x. This is a vector equation with polynomials. So a quicker way to set up this equation is I can put a coefficient of P1 in the first column, 1, 1, 1. Put a coefficient of P2 in the second column, 1, 0, 1. Because coefficient of x here is 0. Coefficient of the constant is 2. Coefficient of x is 0. Coefficient of s squared is 1. And for P3, I put a coefficient in the third column. Coefficient of constant is 0. Coefficient of x is 1. Coefficient of s squared is 2. Then I put a coefficient of p in the last column. Put a coefficient of p in the last column. Coefficient of p is 4, 2, and 9. That's a quicker way to set down this vector equation. For polynomials, I put a coefficient of P1, P2, P3 in the first 3 columns, and then put a coefficient of P in the last column. Then I can solve an equation for K1, K2, K3. Here we can use the Gauss-Jordan elimination. So let's use Gauss-Jordan elimination to reduce the matrices. In the first row, that's a leading one. We try to make all entries below leading one to be 0. I can first of all multiply row 1 by -1, add it to row 2. I get 1, 2, 0, 4 in the first row. 0, -2, 1, -2 in the second row. Next, I try to make 0 here. So I can multiply first row by -1, add it to the third row. I get 0, -1, 2, and 5 in the third row. Next, in the second row, I try to make leading one here. What I can do is I can interchange row 2 and row 3. I get 1, 2, 0, 4 in the first row. 0, -1, 2, 5 in the second row. 0, -2, 1, -2 in the third row. Next, I try to make positive 1 here. So I multiply second row by -1. Multiply second row by -1. First row stays the same. 1, 2, 0, 4. Second row is 0, 1, -2, -5. Leave the third row the same. I get 0, -2, 1, -2. Next on leading 1. I try to make all entries above or below leading 1 to be 0. So I can multiply second row by -2, add it to the first row. Multiply second row by -2, add it to the first row. I get 1, 0, 4. 14. Leave the second row the same. I get 0, 1, -2, -5. Next, try to make 0 here in the third row. I can multiply second row by 2, add it to the third row. I get 0, 0. Multiply second row by 2, add it to the third row. It's -3 here. Multiply second row by 2, add it to the third row. I get -12. Next, in the third row, try to make leading 1 here. I can divide the third row by -3. Take -1/3 times the third row. I get 1, 0, 4, and 14 in the first row. 0, 1, -2, -5 in the second row. 0, 0, 1, and 4 in the third row. Next, that's a leading one here. I try to make all entries above leading one to be 0. So I can multiply the third row by -4 added to the first row. I get 1, 0, 0, -2. Next, I can multiply third row by 2. I can multiply third row by 2 added to the second row. I get 0, 1, 0, 3, and leave the third row the same. I get 0, 0, 1, 4, which means K1 equal to -2, K2 equal to 3, K3 equal to 4. If I find K1, K2, K3, if I can find K1, K2, K3, it means I can write P of X as a linear combination of P1, P2, P3. And the coordinate vector of P with respect to S is K1, K2, K3. Here, K1, K2, K3 is -2, 3, and 4. That's the coordinate vector of P with respect to S. With respect to B, sorry. We try to find coordinate vector of P with respect to B. So coordinate vector of P with respect to B is -2, 3, and 4. We can check the answer. If we take -2 times P1 plus 3 times P2 plus 4 times P3, we must get P of X. Let's check. If I take -2 times P1 of X plus 3 times P2 of X plus 4 times P3 of X, if we calculate everything correctly, we must get P of X. We can check. -2 times P1 of X. P1 of X is 1 plus X plus S squared. Plus 3 times P2 of X. P2 of X is 2 plus S squared. Plus 4 times P3 of X. P3 of X is X plus 2S squared. I can first of all distribute -2. I get -2 minus 2x minus 2s squared plus 6 plus 3x squared plus 4x plus ax squared. If we combine like terms, let's combine the constant first. -2 plus 6 is 4. -2x plus 4x is 2x. -2x squared plus 3x squared is 1x squared. 1x squared plus ax squared is 9x squared. That's the same as P of X. That's how we check the answer. Next example, let M equal to 1, 4, 2, 7 be a matrix in M22. M22 is a set of all 2 by 2 matrices. Part A, let S be the standard basis in M22. Find the coordinate vector of M with respect to S. Here, how can we find the coordinate vector of M with respect to S? S is the standard basis of in M22, which means S has 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, 4 vectors. In order to find the coordinate vector of M with respect to S, I try to write M as a linear combination of these 4 vectors in S. We try to write M as a linear combination of these 4 vectors in S. Here, what can we do here? M is 1, 4, 2, 7. How can we write M as a linear combination of these 4 vectors? Let me call these 4 vectors V1, V2, v3, and v4. How can we write M as a linear combination of these four vectors? For small numbers, we can try it out. So M can be written as 1, 0, 0, 0 plus 0, 4, 0, 0 plus 0, 0, 2, 0 plus 0, 0, 0, 7. The first matrix can be written as 1 times 1, 0, 0, 0. Second matrix can be written as 4 times 0, 1, 0, 0. The third matrix can be written as 2 times 0, 0, 1, 0. And the fourth matrix can be written as 7 times 0, 0, 0, 1. And here, 1, 0, 0, 0 is the same as V1. 4 times 0, 1, 0, 0, that's the same as 4 times V2. That's the same as V3. So plus 2V3 plus 7 times V4. This is V4. So here I write M as a linear combination of V1, V2, V3, V4. The corresponding scalars is 1, 4, 2, 7. Therefore, the coordinate vector of M with respect to S is these four scalars, 1, 4, 2, 7. That's the coordinate vector 1, 4, 2, 7. That's the coordinate vector of M with respect to S. Part B. Let B be the set of four matrices. Let B be the set of four matrices. 1, 2, 3, 4. 1, 0, 0, negative 3. 2, 3, 3, 2. Negative 1, 1, negative 2, 2. Let B be a basis in M22. Let B be a basis in M22. Find a coordinate vector of M with respect to B. Find a coordinate vector of M with respect to B. What can we do here? In order to find a coordinate vector of M with respect to B, we first of all try to write M as a linear combination of these four vectors in B. We first of all try to write M as a linear combination of these four vectors in B. So I first of all set M equal to K1 V1 plus K2 V2 plus K3 V3 plus K4 V4. Assume these four vectors, they are V1, V2, V3, V4. Assume the vectors in B are V1, V2, V3, V4. We try to write M as a linear combination of V1, V2, V3, V4. So a quicker way to set down this vector equation is we put the entries in V1 in the first column. I get 1, 2, 3, 4. Put the entries in V2 in the second column. I get 1, 0, 0, negative 3. Put the entries in V3 in the third column. I get 2, 3, 3, 2. And put the entries in V4 in the fourth column. I get negative 1, 1, negative 2, 2. And then put the entries in M in the last column. Put the entries in M in the last column. Entries in M is 1, 4, 2, 7. Then we can use Gauss-Jordan elimination to solve the equations for K1, K2, K3, K4. We can use Gauss-Jordan elimination to solve an equation for K1, K2, K3, K4. That's the leading one here. We try to make all entries below leading one to be 0. So all I can do here is I can multiply first row by -2, add it to the second row. I can multiply first row by -2, add it to the second row. So first row stays the same. I get 1, 1, 2, -1, and 1. Multiply first row by -2, add it to the second row. I get 0, -2, -1, 3, and 2. In the third row, I try to make 0 here. So I multiply first row by -3, add it to the third row. I get 0, -3, -3, and 1. Last entry is -1. Next, in the fourth row, try to make 0 here. I can multiply first row by -4, add it to the fourth row. I get 0, -7, -6, +6, and +3. Next, in the second row, try to make the first non-zero entry to be 1 here. How can I make 1 here? I can multiply the third row by -1, add it to the second row to make 1 here. I can multiply the third row by -1, add it to the second row. So first row stays the same. 1, 1, 2, -1, and 1. Multiply third row by -1, add it to the second row. I get 0, 1, 2, 2, 3. Leave the third row the same. I get 0, -3, -3, 1, -1, 0, -7, -6, 6, 3. Next, that's the leading one here. I try to make all entries above or below leading one to be 0. Here I can multiply second row by -1, add it to the first row. I get 1, 0, 0, -3, -2. I leave the second row the same. I get 0, 1, 2, 2, 3. Next, I try to make 0 here. I can multiply second row by +3, add it to the third row. I get 0, 0, +3, +7, and 8. Next, in the fourth row, try to make 0 here. I can multiply the second row by 7, add it to the fourth row. I get 0, 0, 14 plus -6 is 8. 14 plus 6 is 20. 21 plus 3 is 24. I try to make 1 here. what I can do is I can divide the fourth row by 4. I can divide the fourth row by 4. If I divide the fourth row by 4, I have a 2 here. I get 0, 0, 2, 5, 6. I try to make 1 here. I can multiply the fourth row by -1, add it to the third row. I can multiply the fourth row by -1, add it to the third row to make 1 here. So first row stays the same. Second row stays the same. For the third row, I multiply fourth row by -1, add it to the third row. I get 0, 0, 1, 2, 2. I leave the fourth row the same. 0, 0, 2, 5, 6. Next, a leading one here. I try to make the entries above or below leading one to be 0. Here I can multiply the third row by -2, add it to the second row. I leave the first row the same. 1, 0, 0, -3, -2. Multiply third row by -2, add it to the second row. I get 0, 1, 0. -4 plus 2 is -2. -4 plus 3 is -1. Leave the third row the same. I get 0, 0, 1, 2, 2. Next, I try to make 0 here. I can multiply the third row by -2, add it to the fourth row. I get 0, 0, 0. -4 plus 5 is 1. -4 plus 6 is 2. Next, a leading one here. I try to make all entries above leading one to be 0. So here I can multiply the fourth row by 3, add it to the first row. I get 1, 0, 0, 0. 6 plus -2 is 4. Next, I can multiply the third row, the fourth row by 2, add it to the second row. I get 0, 1, 0, 0. 2 times 2 is 4. 4 plus -1 is 3. Next, I can multiply the fourth row by -2, add it to the third row. I get 0, 0, 1, 0. That's -4 plus 2 is -2. And leave the fourth row the same. I get 0, 0, 0, 1, 2. After solving the equation, you can see that here, K1 is 4. K2 is 3. K3 is -2. K4 is 2. That's K1, K2, K3, K4. Which means M can be written as K1 times V1 plus K2 times V2 plus K3 times V3 plus K4 times V4. M equal to 4V1 plus 3V2 plus -2V3 plus 2V4. So the coordinate vector of M with respect to B the coordinate vector of M with respect to B is a vector formed by these four scalars. It's a vector formed by these four scalars. 4, 3, -2, 2. That's the coordinate vector of M with respect to B. We can check the answer. How can we check the answer? If I take 4 times V1, 3 times V2, -2 times V3, and 2 times V4, we must get exactly the same matrix as matrix M. Let's check. If I take 4 times V1 plus 3 times V2 plus -2 times V3 plus 2 times V4 what do we get here? If I distribute 4, I get 4, 8, 12, 16. If I distribute 3, I get 3, 0, 0, -9. If I distribute -2, I get -4, -6, -6, and -4. If I distribute 2, I get -2, 2, -4, and 4. Then add the corresponding entries. 4 plus 3 is 7. 7 plus -4 is 3. 3 plus -2 is 1. Second entry, a plus 0 is a. A plus -6 is 2. 2 plus 2 is 4. Third entry, 12 plus 0 is 12. 12 plus -6 is 6. 6 plus -4 is 2. The fourth entry, 16 plus -9 is 7. 7 plus -4 is -3. -3 plus 4 is 7. That's the same as matrix M. That's how we check the answer. So that's the coordinate vector of M with respect to B. Next example, let B and C be two bases in P2, and let P of X be a vector in P2. If the coordinate vector of P with respect to B is 4, 1, -3, find the coordinate vector of P with respect to C. What can we do here? We try to find the coordinate vector of P with respect to C. In order to find the coordinate vector of P with respect to C, let's find P first. We know that the coordinate vector of P with respect to B is 4, 1, 3. 4, 1, -3. That means P of X equal to 4 times the first vector, 1 times the second vector, plus -3 times the third vector. Let's find vector P first. If the coordinate vector of P with respect to B is 4, 1, -3, that means P of X equal to 4 times the first vector in basis B, 1 times the second vector in B, -3 times the third vector in B, and then add it up. Next, let's multiply. 4 times 2 is A. 4 times -x is -4x squared. 1 times 1 is 1. 1 times 3x is 3x. -3 times 3 is -9. -3 times 2x is -6x. -3 times -x squared is +3x squared. Next, let's combine like terms. A plus 1 is 9. 9 minus 9 they can cancel. 3x plus -6x is -3x. negative 4x squared plus 3x squared is negative x squared. That's P of x. Next, we try to find a vector coordinate. We try to find a coordinate vector of P with respect to C. So I set P of x equal to K1 times P1 plus K2 times P2 of x plus K3 times P3 of x. Let's call these three vectors in C to be P1, P2, P3. Let's call these three vectors P1, P2, and P3. So a quick way to set up this vector equation is I put the coefficients of P1 in the first column, I get 1, 1, 1. Put the coefficient of P2 in the second column, I get 3, 2, 1. Put the coefficient of P3 in the third column, I get negative 1, negative 3, and 0. And then put the coefficient of P in the last column. Coefficient of P is 0, negative 3, negative 1. Then solve this equation for K1, K2, K3. We can use Gauss-Jordan elimination. We can use the Gauss-Jordan elimination. So here, that's a leading one. I try to make all entries below leading one to be 0. So I can multiply first row by negative 1. Add it to the second row. I get 1, 3, negative 1, 0. 0, negative 1, negative 2, negative 3. I try to make 0 here, so I can multiply first row by negative 1, add it to the third row. I get 0, negative 2, one, negative 1. Next, in the second row, try to make leading 1 here. So I can multiply second row by negative 1. Here, I leave the first row the same. I get 1, 3, negative 1, 0. Multiply second row by negative 1. I get 0, 1, 2, 3. Leave the third row the same. I get 0, negative 2, 1, negative 1. Next, I can multiply second row by negative 3. Add it to the first row. I get 1, 0, negative 6 plus negative 1 is negative 7, negative 9 plus 0 is negative 9. I leave the second row the same. I get 0, 1, 2, 3. Next, I can multiply second row by 2. Add it to the third row. Four plus 1 is 5. 6 plus negative 1 is 5. Next, in the third row, try to make leading 1 here. I can divide the third row by 5. I get 0, 1, negative 7, negative 9 in the first row. I leave the first row the same. Leave the second row the same. I divide the third row by 5. I get 0, 0, 1, 1. That's a leading 1 in the third row. We try to make all entries above leading 1 to be 0. So I can multiply third row by 7, add it to the first row. So I get 1, 0, 0, negative 2. Next, I can multiply third row by -2, add it to the second row. I get 0, 1, 0. And leave the third row the same. I get 0, 0, 1, 1. So based on the equation here, we know that K1 is -2, K2 is 1, K3 is 1. So here K1 is -2, K2 is 1, K3 is 1. That means P of x equal to -2 times P1 plus 1 times P2 plus 1 times P3 of x. So the coordinate vector of P with respect to C is these three coefficients, -2, 1, and 1. Here we change P from base B to base C. This procedure here is called the change of bases. So that's one way to change bases. Next, I'll show you a different way to change bases. Let's consider the following. Let V be a finite dimensional vector space with W belong to V. And let B and C be bases in V. Since all bases in V must have the same number of vectors, here we assume both B and C have n vectors. Next, assume the coordinate vector of W with respect to B is K1, K2 up to Kn, and the coordinate vector of W with respect to C is L1, L2 up to Ln. Next, I'll show you how to change bases from B to C. First of all, since C is a basis in W, then all vectors in V can be written as a linear combination of V1, V2, Vn. So U1, U2, Un, they can all be written as a linear combination of V1, V2, Vn. Since C is a basis in V, then all vectors in V can be written as a linear combination of V1, V2, Vn. So U1 can be written as a linear combination of V1, V2, Vn. So assume U1 is A11 V1 plus A21 V2 plus AN1 Vn. Since U1, U2, Un, they all belong to V, all vectors in V can be written as a linear combination of U1, U2, Un. And similarly, U2 can be written as A12 V1 plus A22 V2 plus AN2 Vn. And similarly, UN can be written as A1n times V1 plus A2n times V2 plus ANN times VN. Next, since the coordinate vector of W with respect to B is K1, K2, Kn, that means W can be written as K1 times U1 plus K2 times U2 plus Kn times Un. So next, for each equation, for the first equation, I'll multiply both sides by K1. For the second equation, I'll multiply both sides by K2. And keep going. For the last equation, I'll multiply both sides by Kn. So for the first equation, I multiply both sides by K1. I get K1 U1. If I multiply the right side by K1, I distribute K1 to every factor. If I multiply the right side by K1, I distribute K1 to every factor. So I get K1 times A11 V1 plus K1 times A21 V2. And keep going, I get K1 times AN1 times Vn. Next, I multiply the second equation by K2 on both sides. I get K2 U2 equal to K2 times A12 V1 plus K2 times A22 V2 plus K2 times AN2 Vn. And keep going, do the same thing, keep going. On the last row, I multiply both sides by Kn. So I get Kun equal to Kn Un, multiply last row by Kn. I get Kn times A1n V1 plus Kn times A2n V2 and plus Kn times ANN Vn. Next, since the coordinate vector of W with respect to B is K1, K2, Kn, that means K1 U1 plus K2 U2 plus Kn Un together is W. So if I add this vector together, if we add both sides together, on the left side, I get W. K1 U1 plus K2 U2 plus Kn Un, I get W. On the right side, what do we get here? On the right side, what do we get here? On the right side, I can combine like terms. So let me continue. On the right side, if I add the first column together, I get A11 K1 plus A12 K2 plus A1n Kn times V1. If I add the first column together, I add this coefficient together. They all have the common factor V1. So factor V1 out, I get K1 A11, K2 A12, Kn A1n. So here I put K the K's on the back. Write A first, write K on the back. I get A11 K1 plus A12 K2 plus A1n Kn. That's the first column. Now if I add the second column, do the same thing. I write A in the front, write K in the back. For the second column, I can factor V2 out. For the second column, I can factor V2 out. Add the scalar together. Add all scalar together. And also, I write A in the front, write K in the back. So for the second column, I get A21 K1 plus A22 K2 plus A2n Kn times V2. That's the second column. Continue in the last column. If I add the last column together, they have common factor Vn. If I pull out Vn, I have K1 AN1, K2 AN2, and Kn ANN. And same thing, I try to write A in the front, write K in the back. So I get AN1 K1 plus AN2 K2 plus ANN Kn times Vn. If I factor Vn out, that's what I get here. And then also we know that the coordinate vector of W with respect to C is L1, L2, Ln. Since the coordinate vector of W with respect to C is L1, L2, Ln, that means W can be written as a linear combination of V1, V2, Vn with coefficients L1, L2, Ln. So W equal to L1 times V1 plus L2 times V2 plus Ln times Vn. Then, since V1, V2, Vn is a basis, W can be written as a linear combination of V1, V2, Vn in exactly one way by unique basis representation. W can be written as a linear combination of V1, V2, Vn in exactly one way. Then, by matching these two equations, we can see that this expression must equal to L1, this expression must equal to L2, and this expression must equal to Ln. So by unique basis representation, A11 times K1 plus A12 times K2 plus A1n times Kn must equal to L1. And this entry must equal to L2. That means A21 K1 plus A22 K2 plus A2n Kn must equal to L2. And keep going. The last entry, A1n K1, AN2 K2, this must equal to Ln. So AN1 K1 plus AN2 K2 plus ANN Kn must equal to Ln. Next, if I try to write this equation as a matrices, what do I get? If I try to write this as a matrices, on the left side, it can be written as A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN, times K1, K2, and Kn. The left side of the equation can be written as a matrix A11, A12, A1n, A21, A22, A2n, AN1, AN2, ANN times the column vector K1, K2, Kn. It's the left side. And the right side can be written as a column vector L1, L2, Ln. So here we can see that if I take K1, K2, Kn, multiply by this matrix, I get L1, L2, Ln. So by doing matrix multiplication, I change the basis from base B to base C. By doing matrix multiplication, I change basis from B to C. So what's the input here is K1, K2, Kn. If I multiply, the output is L1, L2, Ln. So by doing matrix multiplication, I change the basis from B to C. And this matrix has a name. It's called a transition matrix. is called a transition matrix from base B to base C, because by doing matrix multiplication, it changes from base B to base C. Note, the above matrix with entries Aij is called the transition matrix. It's called a transition matrix from base B to base C. Denoted by P sub B to C. This symbol denotes this matrix. This symbol denotes this matrix. So this matrix P sub B to C, the transition matrix from B to C, times the coordinate vector of W in B. The transition matrix from B to C times the coordinate vector of W in B equal to this. This is the coordinate vector of W with respect to base C. So if I take this matrix, multiply by this column vector, I get this column vector. I change from base B to base C. This is a matrix. This is an n by n matrix. P sub B to C, that's called a transition matrix from B to C. This represents a matrix. This symbol represents a matrix. And similarly, if we try to change the base from C to B, we can also find a transition matrix. If we try to change the bases from C to B, by doing the same procedure, we can find another transition matrix. So similarly, there exists a transition matrix from C to B. If we try to change from base C to base B, we can find another transition matrix. So there exists a transition matrix from base C to base C, from base C to base B. Let's call this matrix Q. Let's call this matrix Q from C to B. Then this transition matrix Q sub C to B. If I take this matrix, multiply by the column vector here, I get this column vector in matrix B. So I take the transition matrix times the coordinate vector of W with respect to C. I get a coordinate vector of W with respect to B. I change the basis from C to B. Now, let's observe these two equations together. If I replace W sub C with the entire equation here, what do we get? Because this entire equation equal to W sub C. If I replace W sub C with this equation here, what do we get? So I get Q times P times W sub B equal to W sub B. B should be outside the parentheses. Then, by associative law, this can be rewritten as Q times P times W sub B equal to W sub B. And we know that the transition matrix from C to B, this is an n by n matrix. The transition matrix from B to C is also n by n matrix. If we multiply two n by n matrices, their product is an n by n matrix. So their product here is an n by n matrix. Since W is arbitrary vector, its coordinate in base B is also arbitrary. This is arbitrary. Since W is arbitrary vector, its coordinate in base B is also arbitrary. And in chapter 1, we know that. For any n by n matrix, if the matrix times x equal to x for all x in Rn, if Ax equal to x, if A times x equal to x for all x in Rn, then A, the matrix A, must be identity matrix. If A is n by n matrix, n times x equal to x for all x in Rn, then matrix A must be the identity matrix. That's all we learned in chapter 1. Apply this theorem here. This is an n by n matrix. If this matrix times the column vector equal to column vector itself for all column vectors, then this must be identity matrix. This must be identity matrix. Hence, the transition matrix from C to B times the transition matrix from B to C is identity matrix. Which means the transition matrix from B to C is invertible. The transition matrix from B to C is invertible. And its inverse is the transition matrix from C to B. Its inverse is a transition matrix from C to B. So, based on this conclusion here, we have the following theorem. Let V be a finite-dimensional vector space with bases B and C if P from B to C is a transition matrix from B to C, if this is a transition matrix from B to C, then this matrix must be invertible. And its inverse is the transition matrix from C to B. So based on this theorem, we know that the inverse of the transition matrix from B to C is a transition matrix from C to B. The inverse of transition matrix from B to C is a transition matrix from C to B. Usually we use P for transition matrix. Write as P from C to B. In the above example, in order to avoid confusion, I use Q, but in general, we use letter P with letter P for transition matrix. In the above example, in order to avoid confusion, I write Q instead of P, but in general, we must use P for transition matrix. So, the inverse of the transition matrix from B to C is always a transition matrix from C to B. In a general vector space, if we try to find a transition matrix, it's not easy. However, if the vector space is Rn, there's an easier way to find a transition matrix. So, in the previous example, assume the vector space V is Rn. In the previous example, assume the vector space V is Rn. We will try to find the transition matrix from base B to base C. I'll show you a way to find the transition matrix from base B to base C. So we try to find the transition matrix from base B to base C. Here, to make the problem a little easier, I'll call base B the old basis. I'll call base C the new basis. Because we are looking for transition matrix from base B to base C, I'll call base B the old basis. I'll call base C the new basis. Here. Base B will be denoted as the old basis. And base C will be denoted as the new basis. try to find the transition matrix from the old basis to the new basis, which means we try to find this matrix A11, A12, A1n, and so on. We try to find this matrix, which means we try to find all entries here, A11, A12, and so on. Try to find all entries here. In order to find entries A11, A21, AN1, since we know these vectors U1, U2, Un, V1, V2, Vn in Rn, we can solve these vector equations for A11, A21, and AN1. Since the base is known, we can solve these vector equations for A11, A21, AN1, and so on. So, in order to solve the vector equations, let's look at the first equation first. In order to solve the vector equation, U1 equal to A11 V1 plus A21 V2 plus AN1 V1. We can set up the following augmented matrix. We can set up augmented matrix as the following. Since these vectors V1, V2, Vn, and U1, they are known, we can put a component of V1 in the first column, put a component of V2 in the second column, and put a component of Vn in the nth column. Then put a component of U1 in the last column. That's the augmented matrix of this vector equation. Next, if we reduce the matrix using the Gauss-Jordan elimination, we can find the scalars A11, A21, and AN1. If we reduce the matrix using the Gauss-Jordan elimination, we can find the scalars A11, A21, and AN1. But if we reduce this matrix using the Gauss-Jordan elimination, what do we get? What do we get here? Since V1, V2, Vn, they are all vectors of Rn. So they have n components, which means we have n rows. And from V1, V2 to Vn, there are n vectors. So we have n columns. Before U1, there are n columns. We have n rows and n columns. This is a square matrix. According to what we learned in the previous class, we know that since V1, V2, Vn, they are bases. They are vectors in a basis. This matrix must be invertible. The determinant of this matrix cannot be 0. This matrix must be invertible. Then, by equivalence statements, since this matrix is invertible, if we reduce it completely, its reduced right echelon form must be identity matrix. If we reduce V1, V2, Vn completely, using the Gauss-Jordan elimination, we must get identity matrix in the reduced right echelon form. And the solution here must be A11, A21, AN1. So the last column must be A11, A21, and AN1. Since the solution must be A11, A21, AN1, it must be the last column. Similarly, the augmented matrix of the second vector equation must be, for the second vector equation, we have U2 equal to A12 times V1 plus A22 times V2 plus AN2 times Vn. For the augmented matrix, we must have V1 in the first column, V2 in the second column, and Vn in the nth column. And for the last column, we have U2 in the last column. If we reduce the matrix using the Gauss-Jordan elimination, the first n columns, U1, U2, Un, must be identity matrix. And the last column must be these scalars, A12, A22, AN2. The last column must be these scalars, A12, A22, and AN2. And continue. The last column and augmented matrix of the last vector equation that's the second one. Continue. The augmented matrix of the last vector equation must be for the last vector equation, it must be V1 in the first column, V2 in the second column, Vn in the nth column, and Un in the last column. Un in the last column. Then, using the Gauss-Jordan elimination, we can find we have In in the first n columns, identity matrix in the first n columns, and the scalars A1n, A2n, AN in the last column. Now, if we observe this augmented matrix, we can see that the first n columns, they are exactly the same. The only difference is the last column. Here we can see that for this augmented matrix, the first n columns, they are exactly the same. The only difference is the last column. So, the above augmented matrix can be combined as one matrix. the above augmented matrix can be combined as one matrix. For all its matrices, since the first n column are exactly the same, the only difference is the last column. We can combine this together as one matrix. So for the new matrix, we have V1 in the first column, V2 in the second column, Vn in the nth column. After Vn, we put U1 as next column. We put U1 followed by U2, U3 until Un. So it'll be V1, V2, Vn followed by U1, U2, Un. Now, if we reduce this matrix using the Gauss-Jordan elimination, what do we get? If we reduce the matrix using the Gauss-Jordan elimination, what do we get? If we reduce this matrix using the Gauss-Jordan elimination, the first n columns, V1, V2, Vn, the first n columns, V1, V2, Vn, will eventually turn out to be In, to be identity matrix. The first n columns will turn out to be In. U1 will be A11, A21 until AN1. If we reduce the matrix using the Gauss-Jordan elimination, U1 become A11, A21, AN1. U2 become A12, A22, AN2. Continue. UN become A1N, A2N, ANN. A1N, A2N, ANN. What is the matrix? What is the matrix? A11, A12, A1N, A21, A22, A2N. What is the matrix? This matrix looks exactly the same as the transition matrix here. A11, A12, A1N, A21, A22, A2N. This is a transition matrix from base B to base C. This is exactly the same as In followed by the transition matrix from B to C. So here we can see that V1, V2, Vn, they are basis vectors in C. V1, V2, Vn, they are basis vectors in C. And C is called the new basis. C is called the new basis. U1, U2, Un, they are basis vectors in B. U1, U2, Un, they are basis vectors in B. And here, B is called the O basis. B is called the O basis. Which means, if we set up the new basis, if we set up the matrix as the new basis, followed by the O basis, then reduce it using the Gauss-Jordan elimination. We will eventually get identity matrix followed by the transition matrix from the old basis to new basis. if we put a new basis here, followed by an old basis, then reduce it using the Gauss-Jordan elimination, eventually we get an identity matrix, followed by a transition matrix from the old base to the new basis. That's how we find a transition matrix in Rn. That's how we find a transition matrix in Rn. Similarly, for transition matrix in Pn or MNM, we do the same thing. Similarly, for the transition matrix in Pn, we can write the coefficients of each vectors. In the basis as column vectors. And for the transition matrix in MMM, we can write the entries of each matrix as a column vector. We can run the entries of each matrix in the basis. As column vectors. In the above matrix. We put a new matrix here, followed by an old matrix. Then use Gauss-Jordan elimination. We get an identity matrix here. What's left here? What's after an identity matrix? It's a transition matrix from the old base to the new basis. So keep this formula in mind. Keep this formula in mind. That's how we find transition matrix in Rn, Pn, and MMN. Next, let's redo example 4 using the transition matrix. In example 4, we have two bases, B and C in P2. We try to derive the coordinate vector of P from base B to base C. So we will consider B as an old basis and C as a new basis. We consider B as an old basis, C as a new basis. Let's find a transition matrix first. For the transition matrix, we first of all set out the matrix using the new basis followed by the old basis. Here, the new basis is C. New basis is C. For polynomials in Pn, we put a coefficient in columns. For polynomials in Pn, we put a coefficient in columns. So for the new basis C, for the new basis C, the coefficient here is 1, 1, 1 in the first column. The coefficient is 3, 2, 1 in the second column. The coefficient is -1, 3, -1, -3, 0 in the third column. That's the coefficient of the new basis. -1, -3, and 0. Those are the coefficients of the new basis. Next, from the old basis do the same thing. For the old basis B, do the same thing. Put the coefficient in columns. We have 2, 0, -1. Second vector we have 1, 3, 0. The third vector is 3, 2, -1. Then, next, reduce the matrix using the Gauss-Jordan elimination. Here, the first row is 1 here. We try to make this a leading 1. We try to make all entries below leading 1 to be 0. So I can multiply first row by -1, add it to the second row. I get 1, 3, -1. First row stays the same. Two, 1, 3. Multiply first row by -1, add it to the second row. I get 0, -1, -2, -2, +2, -1. Next, so to make it 0 here. So I multiply first row by -1, add it to the third row. I get 0, -2, +1. -2 plus -1 is -3. -1 plus 0 is -1. -3 plus -1 is -4. Next, in the second row, try to make leading 1 here. So I can multiply second row by -1. I can multiply second row by -1. So first row stays the same. 1, 3, -1. 2, 1, 3. Multiply second row by -1. I get 0, 1, 2. 2, -2, and 1. Leave the third row the same. 0, -2, 1. -3, -1, -4. That's the leading 1 here. We try to make the entries above and below leading 1 to be 0. So next, I can multiply second row by -3, add it to the first row. Multiply second row by -3, add it to the first row. I get 1, 0, -6, plus -1 is -7. -6 plus 2 is -4. +6 plus 1 is 7. -3 plus 3 is 0. Leave the second row the same. I get 0, 1, 2, 2, -2, 1. Next, I can multiply the second row by 2, add it to the third row. I get 0, 0. 4 plus 1 is 5. 4 plus -3 is 1. -4 plus -1 is -5. 2 plus -4 is -2. Next, in the third row, try to make leading one here. Here, the only possibility is I divide the third row by 5. That's the only possibility. I divide the third row by 5. So I get 1/5 row 3. So first row, second row stays the same. I get 1, 0, -7, -4, 7, 0, 0, 1, 2, 2, -2, 1. Divide the third row by 5. I get 0, 0, 1. 1/5. -1, -2/5. That's a leading one here. We try to make all entries above leading one to be 0. So I can multiply the third row by 7, add it to the first row. Multiply the third row by 7, add it to the first row. I get 1, 0, 0. Multiply the third row by 7, I get 7/5 plus -4. -4 plus 7/5. That's -20 plus 7/5, which is -13/5. Multiply the third row by 7, add it to the first row, I get 0 here. Multiply by the third row by 7, add it to the first row, I get -14/5. Next, I can multiply the third row by -2, add it to the second row. I get 0, 1, 0. I get 2 plus -2/5, which is 10 minus 2/5, which is 8/5. -2 times -1 is 2. 2 plus -2 is 0. -2 times -2/5 is 4/5. 4/5 plus 1 is 9/5. The third row stays the same. I get 0, 0, 1. 1/5, -1, and -2/5. Once I make the first matrix to be identity matrix, the matrix after identity matrix is a transition matrix from the old base to the new basis. The matrix after identity matrix is a transition matrix from the old basis to the new basis. So this is a transition matrix from the old base to the new basis. That's a transition matrix from B to C. B is an old basis, C is a new basis. And equal to -13/5. Zero, -14/5. 8/5, 0, 9/5. 1/5, -1, -2/5. That's the transition matrix. Next, let's compute the coordinate vector of P in C. For the coordinate vector of P in C, we use the transition matrix from B to C times the coordinate vectors of P in B. This P and this P, they are not the same thing. This is lowercase p. This is capital P. They're not the same thing. This P is a vector. This P is a vector, and this P stands for the transition matrix. That's the coordinate vector of P in B. That's a transition matrix. The transition matrix is this matrix: -13/5, 0, -14/5, 8/5, 0, 9/5, 1/5, -1, -2/5. The coordinate vector of P in B here is given. E4 is given. The coordinate vector of P in B is 4, 1, -3. Here we write it as a column vector. Run the coefficient vector as a column vector. We get 4, 1, -3. Next, multiply. Use row times columns. Row times columns. -13/5 times 4 is -52/5. Plus 0 plus 42/5. -52/5 plus 42/5 is -10/5. -10/5 is -2. Next, row times columns. 4 times 8/5 is 32/5. 1 times 0 is 0. -3 times 9/5 is -27/5. 32/5 plus -27/5 is 5/5, which is 1. Next, row times column. 4 times 1/5 is 4/5. 1 times -1 is -1. -3 times -2/5 is 6/5. Here, 4/5 plus 6/5 is 10/5, which is 2. -1 plus 2 is +1. So the coordinate vector of P. So the coordinate vector of P in base C is -2, 1, -1. That's the coordinate vector of P in base C. Let's match what we have here. We also get -2, 1, and 1. So that's another way to change bases. But which way is better? Which way is better? In general, if we only change bases for one vector, then the first way is easier. If we only change bases for one vector, the first way is easier. But if we change bases for a lot of vectors, the second way will be easier. We find the transition matrix, then take each vector, multiply by the transition matrix. We get a coordinate vector in the new basis. So if we need to change bases for only one vector, the first way is easier. If we need to change bases for a lot of vectors, the second way will be easier. Next example, let B and C be bases in R2. Part A, find the transition matrix from B to C, and the transition matrix from C to B. Part B, let the coordinate vector of V in basis B be 1, -2. Find the coordinate vector of V in basis C using the transition matrix. Let's do part A first. Find the transition matrix from B to C. For the transition matrix from B to C, we treat B as an old basis and treat C as a new basis. When we set out the matrices, run the new basis first. Run the component of the new basis first. Here we treat C as a new basis. So run the component in C first. In C, there are two vectors, 1, 3 and 2, 5. Put each vector in columns. We get 1, 3, 2, 5. That's the new basis. And then for the old basis, we have basis B. And there are two vectors, 2, -3 and 3, -4. Next, do the Gauss-Jordan elimination. Try to make the first part of the matrix to be the identity matrix. So there's a leading one here. Try to make the entry below leading one to be 0. So I can multiply the first row by -3 added to the second row. I get 1, 2, 2, 3, 0, -6 plus 5 is -1, -6 plus -3 is -9, -9 plus -4 is -13. Next, in the second row, try to make DD1 here. I can multiply second row by -1. So first row stays the same. I get 1, 2, 2, 3. Second row is 0, 1, 9, 13. Next, we try to make 0 here. So I multiply second row by -2, add it to the first row. Multiply second row by -2, add it to the first row. I get 1, 0, -18 plus 2 is -16. -26 plus 3 is -23. Second row stays the same. I get 0, 1, 9, 13. Once I make this identity matrix, what's after that is a transition matrix from B to C. So the transition matrix is the matrix after an identity matrix. That's -16, -23, 9, and 13. That's a transition matrix from basis B to basis C. Next, let's find a transition matrix from C to B. For the transition matrix from C to B, we treat C as an old basis and B as a new basis. When we set down the matrices, write the new basis first. So for the new basis, write components in vector B in basis B first. First column is 2, -3. Second column is 3, -4. Put each vector in columns. Put each vector in columns. That's the new basis. The old basis is basis C. For each vector, but write in columns. I get 1, 3, 2, 5. Next, reduce the matrices. Here we try to avoid fractions. So I can add the second row to the first row. And the second row to the first row. I get -1, -1, 4, 7. And leave the second row the same. I get -3, -4, 3, 5. Next, try to make DD1 here. So I multiply first row by -1. I get 1, 1, -4, -7. Leave the second row the same. I get -3, -4, 3, and 5. Next, I can multiply first row by 3, add it to the second row. Multiply first row by 3, add it to the second row. Here, leave the first row the same. I get 1, 1, -4, -7, 0, -1, -12 plus 3 is -9, -21 plus 5 is -16. Next, in the second row, try to make DD1 here. So I multiply second row by -1. First row stays the same. You get 1, 1, -4, -7. Second row is 0, 1, 9, 16. Next, I multiply second row by -1, add it to the first row. I get 1, 0. -9 plus -4 is -13. -16 plus -7 is -23. Second row stays the same. I get 0, 1, 9, 16. So that's a transition matrix from basis C to basis B. The transition matrix is the matrix after identity matrix. I get -13, -23, 9, and 16. So that's a transition matrix from C to B. That's a transition matrix from B to C. That's a transition matrix from C to B. If we calculate everything correctly, they must be the inverse of each other. If we calculate everything correctly, they must be inverse of each other. Let's check. If I take the transition matrix from B to C times the transition matrix from C to B, what do we get? We get -16, -23, 9, 13. Times the transition matrix from C to B. That's -13, -23, 9, 16. If they are inverse of each other, when we multiply, we must get a 2 by 2 identity matrix. Let's check. Take row times column. Row times column. -16 times -13. I get 208. -23 times 9. I get 207. So 208 minus 207 is 1. Next, row times column. -16 times -23 plus -23 times 16. They are inverse of each other. They can cancel. We get 0. Next, row times column. 9 times -13 plus 13 times 9. Again, they are inverse of each other. They can cancel. We get 0. Next, row times column. 9 times -23. I get -207 plus 13 times 16. I get 208. 208 plus -207 is +1. So when we multiply, we get an identity matrix. That means these two matrices, they are inverse of each other. That's part A. For the transition matrix from B to C and from C to B. Part B. Let the coordinate vector of V in basis B be 1, 2. Find the coordinate vector of V in basis C. So we know that that's the transition matrix from B to C. If we try to change the base from basis B to basis C, take the transition matrix times the coordinate vectors in matrix B. We get the coordinate vectors in matrix C. So the coordinate vector in matrix C is the transition matrix from B to C times the coordinate vectors in matrix B, in basis B. So we take the transition matrix from B to C, which is this matrix, -16, -23, 9, and 13. Times the coordinate vectors of V in B. That's 1, -2. Put in columns, write it as a column vector. I get 1, -2. Then multiply. Take row times column. I get -16, plus 46. Negative 16 plus 46 is positive 30. Next, take row times column. We get 9 plus negative 26. 9 plus negative 26 is negative 17. So, the coordinate vector of V in basis C is 30, negative 17. That's the coordinate vector of V in basis C. Now, how can we check the answer? How can we check the answer? If we want to check the answer, we can change the basis back to basis C. We can change the coordinate vector back to basis B. If we try to check the answer, we can try to change the basis back to basis B. So this is a coordinate vector in basis C. If we try to change it back to basis B, we can use this transition matrix here. So for the coordinate vector of V in basis B, I take the transition matrix from C to B times the coordinate vector of V in basis C. When we multiply, change the base from C back to B. The transition matrix from C to B here is negative 13, negative 23, 9, and 16. Times the coordinate vector of V in basis C. Here, write it as a column vector. We have 30, negative 17. Let's multiply. Take row times column. Row times column. Negative 13 times 30 is negative 390. Negative 23 times negative 17. 7 times 3 is 21. 1 times 23 is 23. I guess 391. Negative 390 plus 391 is 1. Then row times column. Row times column. 9 times 30 is 270. 16 times 17. I get 172. 272. This is negative. So 270 minus 272 is negative 2. Which means the coordinate vector of V in basis B is 1, negative 2. That's exactly the same as what we have in the beginning. So that's correct. That's how we check the answer. By changing it back to basis B.